All right, so for this first one, 22 minus 35 divided by 7 times 2 plus 4. Remember, we've got order of operations, and we wrote it this way. Who can remind me why we wrote the multiplication and division and the addition and subtraction next to each other? Caleb?
Because multiplication and division comes before addition.
Yep. You're right. Multiplication and division comes before addition and subtraction, but why did we write these side by side instead of up and down?
Because if they're
Yeah, so when we get to this level of multiplication and division, we're simply going left to right. So it doesn't mean that all multiplication is going to happen before all addition. Whatever shows up first, left to right. So for this first one, we don't have parentheses, we don't have exponents. So what's the very first step we should take in solving that? Ross.
I would do, you would do 75 by 35.
35 divided by 7. That's the first multiplication and division left to right, which gives us 5. And then remember, you should just be bringing down everything you haven't used yet. Now what's our next piece according to order of operations, Anna?
5 times 2.
Yep, finish that multiplication and division, and I'm bringing down the 22 minus and the plus 4. Now all I have left is addition and subtraction, which means I'm just going left to right from here on out. So 22 minus 10 is 12. 12 plus 4 is 16. Should have been your first answer there. Okay. All right, for the second one, who can remind us that 5 that's attached to the parentheses, Olivia, what does that mean?
It means multiply it.
Yeah, that is a symbol for multiplication. So we're multiplying 5 by whatever we get in those parentheses. I've had a lot of people ask over the last couple of days, can I put a multiplication symbol here to remind me that I'm multiplying? Yes, you can absolutely change or add that multiplication sign as a visual for yourself. So we're going to start in those parentheses with the exponent 4 to the third, which is 64. And then finish those parentheses. 64 minus 8 is 56. Once I get that parentheses down to just one number, you can leave the parentheses there or you can drop them. Personal preference, whatever you choose. And then our final step, 5 times 56. 280. Very good. All right, before we get into that evaluating expressions worksheet, we're going to get formatives back. But before that, I've got a really good joke for you guys. Ready?
I'm too square.
Oh gosh, people Magnus, don't act like you didn't think that was the funniest thing you've heard all day. Who can read it out loud and read it so that it will be funny? Lilia.
I have a scary joke about math. I'm too square to say it.
I have a scary joke about math, but I'm too squared to say it. Okay, thank you. You are the first class that genuinely humored me and laughed, even if you didn't think it was funny.
I didn't think it was funny. That was actually funny.
Magnus thought it was the funniest thing he's heard all day. He just forgot to laugh. He was so blown away with how funny it was that he forgot to laugh. Yeah, that's good, right? Okay. All right, real quick, these are the problems from your formative. I'm going to pass back to you if I have your formative. Give me a second to pass those back, and then I'm going to point out just a couple of places where people were going wrong on these. A lot of the same common mistakes happening, so give me a second. All right, for the first one, a couple of mistakes that I saw happening on the first one. First of all, I had a lot of people telling me that 3 plus 2 was 6. Oopsies, it's not. That's actually 3 times 2, friends. It's 3 plus 2 is 5. And then a handful of people were still, when we've got the number in front of the parentheses, we're turning that into 45. Remember, invisible multiplication there, that's 4 times 5. So that one should have given you 20 minus 7, which was 13. Overall, not as many mistakes on that one. The second one, though, is where people were like, I don't know what's going on here. Okay, so let's look at this together, and I want you to compare. If this one is circled on your paper, you missed it, figure out which step or which line you went wrong. So starting with parentheses, we didn't have any. Jumping to exponents, we're going to do 2 to the third, which is 8. And then I am bringing down everything I haven't used yet. Again, this is important that you are bringing it down so that you can see the new problem you have.
Wait, didn't you just use 3?
I used 2 to the third power, which was... Oh, yeah. Thank you, Ross. Better? Yeah, I use the exponent, so I don't want to put it there. Good. All right, so now my exponents are done. I'm at this level of multiplication and division. I should be working left to right at this stage. So a ton of people did 3 times 8 next. That is not what shows up first, left to right with multiplication and division. What should I be doing first? Yeah, which is 29. And then I'm bringing down the times 8 and the plus 28. Multiplication should be happening next. Is that what, 232? Anyone have?
Yeah, 232.
Because I graded 77 of these. So when you grade the same problem over and over, sometimes the numbers just stick with you. And then 260. But I also can do a lot of it mental math. It comes with age, Molly. When you get to my age, you forget names, but you get really good at math. It's a great compromise. All right. Are we good on this one? Those of you who missed this one, do you see where you went wrong?
Yeah.
Okay, and also, do you see how when I write out each step and I'm bringing it down, it's pretty easy to see what's changing from line to line, and I'm not skipping and trying to do multiple things at once. Show me step by step what you're doing, okay? This last one, overall, pretty good job. What does that long line mean? Division. So get one answer or one number on the top. So that gives us 47 plus 5 over 2, which is 52 over 2. Once we get it down to that stage where it's one thing over another thing, we can divide, which is 26. Okay? If you didn't get that far, not a huge deal. Okay? All right, if I just pass that back to you, go ahead and put that in your math folder. We're going to move on to just a quick practice on solving expressions with substitution. So that worksheet I had you pull out at the beginning of class, it looks like this is where we're going to focus. So in just a minute, I'm going to let you move around. If you'd like to work with somebody, you could also work independently. Looking at the front of this worksheet, do you have space on the front to do good order of operations problems? No. So what you're going to do, and I will even leave this up so if you don't want to flip back and forth, but you're going to show your work on the back. Here's the issue that some people have been running into today. When you're doing your work on the back, I had people that were like, I'm going to do this problem here, and this one here, and then this one here, and this one here, and this one here, and then they're like, well, I got number 7 wrong. And I go, okay, where did you do it? And they flip it over, and they're like, I don't know which one of these is 7. Well, that's not super helpful then. Okay, so what I want you to do, not only are you focused on the math, but start trying to organize your work neatly. So I'm going to start in the top left corner of my paper, and I'm going to label it number 1, and I'm going to do order of operations and solve and get an answer and circle it. Then I'm going to label the next one right underneath it, number 2. And I'm going to do my work and answer, circle it. Then I'm going to number 3, and I'm working my way down my page. And then maybe I have a second column where I'm working my way down my page, okay? But if you're just randomly putting numbers all over the place, that's not super helpful. Work on organizing and having nice, neat work so you can real quickly go back and say, okay, if I missed number 7, where's number 7? Oh, that's this one right here. I numbered it number 7. Where's my mistake? Okay? A giant piece of paper? No. But you do have your paper, which the back side is blank. So, just to review, Molly, I'll get your question in a second. How this works, number 1 says 5x plus 9y when x is 8 and y equals 11. So the first thing I should see is that you have rewritten it. 5x means 5 times x, and 9y means 9 times y. So I'm rewriting it with those numbers substituted in, and then I'm just going to solve using order of operations. So multiplication and multiplication, and then I can add those together. This is what I would have on the back for number 1. Then I would set up number 2. But this line where I haven't solved anything yet, I've just substituted in, should be where I start for each of these. Okay? Molly, you had a question?
I was wondering if instead of going in the back, we'd be able to use our notebooks.
You could. That's fine too. I'm going to leave this up, so if you don't want to do the flipping back and forth, all the problems will be up on the board. You can just look up here. Okay, so let's take about 10 to 12 minutes to see how many of these you can do. Newsflash, I did number 1 on the board to show you as an example, so you actually only have 8 left. And then we'll check in about 10 or 12 minutes and then we'll move on, okay? All right, so if we're looking at word problems, this is the process I want you to use for writing expressions, word problems. So first, you're going to have to read the problem. Duh. Okay? After you read the problem, you have to determine what it's asking you to write an expression to represent. So a lot of times what's hard is we read a problem and we want to just start picking variables to represent everything, but sometimes the whole expression is going to represent an unknown quantity. I'm going to talk you through this in a second. So figure out what it's asking you to write an expression to represent, and then within that, what is the other unknown quantity? What do we need to write a variable for to help us find what that expression is? And then we're going to write the expression. So let's walk through. I've got 3 of these we're going to walk through together. First one says, cards are sold for $5 each at a team fundraiser. Weekly expenses are $16. Write an expression for how much the team earns in a week for any number of cards sold. So our entire expression, the whole big thing, is going to represent how much money this team earns. So I'm not going to pick a variable for how much the team earns because the whole expression I write is going to represent that. But within their earnings, what is the unknown? What's going to impact how much they earn? That's going to be a variable quantity here. What's going to impact how much they earn? That's going to be a variable. Perfect. Yes. So we're going to start by identifying our variable, and Briley told us correctly, it's how many cards they sell. If they're selling cards and getting $5 for cards sold, they're going to earn a different amount of money if they sell 2 cards versus if they sell 100 cards, right? So the very first thing for these word problems is you're going to pick a variable. I'm going to say C because we're talking about cards. But I'm not going to say C equals cards. What specifically about the cards is unknown that we're trying to write the variable for? Caleb? Yeah, so how many are sold? So I'm going to say C is going to represent the number of cards sold. Because we don't know the cost, we don't know the color of the cards, we don't know the size of the cards, we don't know what kind of card, but specifically to this problem, we're looking at how many cards are sold, okay? So I've identified my variable. Now I need to write an expression to show this. If the team is making $5 for every card, let's ignore the second part for right now. How do I show that they're making $5 for every card? Ross?
You like put that like on the thing you put like a card is equal to $5.
So how do I show that mathematically? Like with what operation? Would I? Good. So I'm going to say 5 times C or 5C. 5 times C, because it's $5 per card, is going to tell me how much I make for all the cards sold. But weekly expenses, it said, are $16. That means that this team is spending $16 maybe on advertising or to print the cards or for the supplies it takes to make the cost. Whatever, it's costing them $16. How do I show that in this expression? Evie?
Minus 16.
Yes, perfect. That's it. That is my final answer for this problem. It's going to get me full credit. I've identified the variable I'm using. I'm saying I'm going to use C, which represents the number of cards sold, and I've written an expression. I'm not solving anything here. I'm just giving the expression to represent this. So $5 times the number of cards minus the $16 in expenses is going to give me however much this team makes. So now, whatever team we're talking about can use this expression to figure out how much money they made. Say week 1 they sell 10 cards. Well, they're going to plug 10 in here and say 5 times 10 is 50, minus 16 is $34. We made $34 this week. Maybe the next week we sell 50 cards. Well, it's a variable, so it changes. Now I can do 5 times 50, $250, minus the $16 in expenses, $234 we made this week. Maybe the next week we only sold 2 cards. 5 times 2 is 10. 10 minus 16, we lost $6 this week. But we can use this every week to see how much money we're making as a team. Does that make sense? Okay, let's look at another one. This one says, Ellie has 12 writing utensils that are either pencils or pens. If A represents the number of pencils she has, so here it's actually telling us what variable we're using. A represents the number of pencils, so there's a free answer. I don't have to figure out what my variable is because it gives it to me. There's 1 point. I'm just recopying that down. A represents the number of pencils she has. Write an expression in terms of A. That sounds really funky. Write an expression in terms of A. That really just means, oops, don't cross it out. That really just means write an expression using A. Use the letter A. That describes the number of pens she has. So we don't know how many pens she has, but it's telling us to write an expression that represents the number of pens. So I'm not going to write a variable for that. The whole thing is going to represent how many pens she has. What expression could I write? If I know she's got 12 altogether, A is the number of pencils, how would we find out how many pens? Ada? Perfect. Oh, sorry. Keep clicking between the highlighter and the pen and I forget. That's it. 12 total. If I take away the number of pencils, what do I have left? The number of pens, which is what my expression is supposed to be. Let's do one more. The width of a box is twice as long as its length. Write an expression to represent the width of the box. So the whole expression is going to represent the width. We're not going to pick a variable for that. What's our variable going to represent, Audrey?
The length.
The length. So L would make sense to use here. When I use L as a variable, I use a cursive L, because if I write a regular L, what's that look like? A 1. When you write variables, you don't want to use capital letters. Get in the habit of using lowercase letters. So I'm going to write a cursive L for the length of the box. If you're like, thanks but no thanks, I don't want to write a cursive L, then pick a different letter and identify it. X is the length of the box. Okay, let's read this. The width of the box is twice as long as the length. So how do I write an expression to represent the width? Audrey?
You do L times, or no, you do L 2.
You're close. Pull the number out front though. 2L. 2 times the length is going to give us the width. Ramona? So great question. Why we don't use capital variables is because the farther you go into math, you're going to find that some of the capital letters actually represent like a whole formula. So for example, a capital B, when we look at geometry, represents the area of the base of a 3D shape. So they're going to start representing other things. So our lowercase variables are what we're going to use in our equations. Good question. All right, questions on these word problems? All right, so to end with combining like terms. Just kidding. The whole point of combining like terms is so that we can simplify an expression down and make it easier to solve. So I want you to think back to the other day, I put that really giant expression on the board that had all these terms in it, right? And you guys looked at it with your eyes bugging out of your head, like, what is that? Okay, you actually, and I will put that in a challenge tomorrow, can start with the substitution we've been doing. You can start solving those. But the point of combining like terms is so that anytime we have things that are like, so all of my A terms, we're going to combine them together, or all of my X terms, put them together so that we don't have to substitute as much. So I'm going to walk you through that process and what that looks like here. What you have to understand, though, is this definition for what like terms are. So like terms are terms that have the same variable raised to the same power or same exponent. So let's look at some examples at the bottom and start wrapping our head around it. So same variable, same letter, raised to the same power, or they don't have a power sometimes, okay? So first example, I've got this expression right here, 2x plus y plus 2y. I'm telling you there are 3 terms in that expression. 2 of those terms are like terms. Which 2 terms there do you think are like terms? Same variable, same power, or no power at all is fine. Caleb?
Like the 2y.
Yeah, so the y and the 2y are considered like terms. They're both y terms, so we're going to be able to start putting those together, okay? What about the next one? 5a minus b plus 3a. There's 3 terms. 2 are like terms. Which 2 are like terms there? Aria.
Is it the 5a and the 3a?
Good. The 5a and the 3a have the same variable, so they're both a terms. We're going to combine those. The last one has 4 terms, but only 3 of them are like terms. Which one doesn't fit with the rest of them? Olivia?
Would it just be x?
Yeah, this one, the minus x and y, it's the same variable. Why doesn't it fit with the rest of them, Olivia?
All the rest of them are raised to the second power.
Yes, all of them, the other ones are x to the second power, even though they're all x's. An x to the second power and an x are two different types of terms. So that minus x is not a like term. These other three would all be able to get combined. Okay, before we get too far, do you see all of these terms that are just a variable? So y minus b and minus x. None of those have coefficients. None of them have numbers in front of them. One thing to know is anytime we have a term that's just a letter, there is an invisible 1 in front of that term. So when it says 2x plus y, that really means 2x plus 1y plus 2y. So if there's no number, no coefficient, it means 1, okay? So let's look at a couple other pairs. You're just going to tell me, are these like terms or not, and then we're going to practice combining them. So 3x and 7x. Yes or no? We can shout these out. Yes. Oops. These ones are. What about 3xy and xy? Yes, those ones are. They both have two variables, but they're the same two variables with the same exponents. What about 4xy and 2xy squared? So why is that one different than the one above it? They're both xy. Audrey?
Because the 2xy has an exponent of 2.
Yep. Because this now has an exponent, they're no longer like terms because this one doesn't. What about 4 and 11?
No. Yeah.
Could we combine 4 and 11?
Yeah. Yes.
What's 4 plus 11? Can we do that?
15.
15. Oh my gosh. Constants are like terms.
Oh.
If it's just a plain number, we can add those together as well or combine those. All right, let's jump over 6x squared and x squared. Yes. 2x and 2y.
No.
Those have the same coefficients. Coefficients don't matter for like terms. It's the variable that we pay attention to. 3x squared and 2x cubed. No. Lilia, you have a question? Or were you going to answer? Answer. Okay, what about the last one? X and z?
Yeah. Yes. Wait, no. Because they're letters. They're not the same.
Not the same variable. They're not the same. Okay, those are not like terms. Arya?
It's because they're letters, but they're not numbers. They're not just plain numbers.
Yeah, if they were just plain numbers, again, like 2 and 5, yes, they'd be the same. But we have to have the same variable or lack of variable there. Okay, so here's what, well, hang on. What does this look like now? Okay, so let's say I have the expression 5x plus 3x. That basically means 5x's plus 3x's. One thing that's going to help you with this is sometimes the idea of a variable is so abstract or so new. Pretend your variables represent an object, and we'll talk through them with an object. So x, xylophone. I have 5 xylophones plus 3 xylophones. What do I get when I add 5 xylophones plus 3 xylophones? I have 8 xylophones. I'm combining those like terms. So all we're doing is adding or subtracting based on the sign the terms that are the same like terms. Lola.
What would we do if like 2 of them are the same, but then a problem one?
We're going to look at it. Yep, we're going to look at that. Okay. All right, let's try another one. 2y plus 7y. So one of the things, hang on, before we get too far, I should have said this, is some of these we're going to add, some are going to subtract. So you're going to start grouping these with symbols. Your first term is not going to have an operation attached to it. It's just going to be 2y. But then the operation symbol is going to get grouped with the term that comes after it. So this is saying we've got, let's say, 2 yo-yos plus 7 yo-yos. What do we have?
9.
We have 9 yo-yos. Okay? Same thing, we've got 8 xylophones plus 12 more xylophones. We have 20 xylophones. We got a whole band. That's a lot of xylophones. You can never have too many xylophones, though. They're a really cool instrument. Okay, so here we've got more terms. Okay, 9a minus 3a plus a. How many of those are like terms?
2.
All of them. They're all a terms. So look at how I'm going to group the operations here. I'm going to say 9a is just 9a. It's the first term. Then it's a minus 3a. That subtraction sign is with the term that comes right after it. And then plus a. So I've got 9 apples, and I take 3 away. What's that give me? We have 6 apples Plus, remember there's an invisible 1 here, plus 1. 7 apples. Okay, this is a great example of why we do this. Let's pretend you went to solve this expression and I told you A is 15. If we don't combine like terms, we're going to have to do 9 times 15 minus 3 times 15 plus 15. We can do that, but it's going to take some time. If we combine like terms first, look, we just have to do 7 times 15 and we're done. So the whole point of combining like terms is to take all of these terms and condense them down together if we can, so it's easier to solve. Audrey.
Wait, I'm confused. How did the 1 get there?
Okay, so 1, that if we have a variable that's by itself and it doesn't have a coefficient, it really means just 1. So that A, because it didn't have a number in front of it, it's just 1. Okay, you can write the 1 in, or you can just in your head know that that's 1. Okay, anytime there's just a variable with no number in front, it means there's 1. Okay, all right, Lola, I think this next one's going to get to the question you were asking. What happens if they're not all like terms? Okay, which of these terms are like terms on this one? Anna? Yep, so I'm going to say 7b and 2b can go together. I'm going to circle the 7b and the minus 2b. The 6 is a constant, it's not a b term. So I'm going to start marking up, well, that's a different type of term. So maybe I'm going to, instead of circle it, I might box it in. Or maybe I underline it. So the different types of terms, I'm going to use different symbols. Because now visually I can see, ooh, all my red circles I'm going to put together. So 7b, 7 bananas, minus 2 bananas.
5 bananas.
That's 5 bananas. The plus 6, the constant, was there anything else I could combine that with? So I'm just going to leave it as a plus 6. That's it. I can't add those because they're not like terms. So when I start this expression, if I look at this, I can look at this and say, okay, how many different types of terms do I see here? Well, I see b terms and I see constants. There are 2 different types of terms happening here. So my final answer should have 2 different types of terms. I should have a b term and a constant. Yes?
Are like these in like normal equation?
Yes. You're going to be using this a lot.
If they don't all have this, would you actually put like the plus 6 if this wasn't? Oh.
Yep. Because it was being added before, so it's still going to be just a plus 6. Because there was nothing I could combine it with. Okay. Let's look at a couple more and then you're going to try some. I have n plus n plus n. I have a nacho, and then I found another nacho. Then I got in my car, and I found a nacho on the bottom of my car. It was a little soggy, but it was still okay. Riley?
So you add a 1 in front of all.
So yeah, I can, if it helps to visualize, those are all 1. 1 nacho plus 1 nacho plus 1 nacho is how many nachos? 3 nachos. Just 3 nachos. Okay? Not a lot of nachos. I was sad. I had only 3 left. And 1 was soggy. It was okay. All right. Which terms are like terms, Anna?
10y and 2y.
Good. 10y and 2y are plain y terms. And then minus 5y cubed is different. So I'm going to not combine that with anything. So combine your y's. I've got 10 yo-yos plus 2 yo-yos. I have 12 yo-yos. Minus 5 cube yo-yos. There was nothing to combine the minus 5y to the third with, so I'm just going to bring it over. That's my answer. I'm done. Yep, I would. Now, if I told you, okay, well, solve when y is 10, then you could go in and plug a 10 in, but I'm not going to have you do all of that at once on your test. Okay? There will be some that you solve, and there will be some that you have to do combining like terms, but we're just going to keep them separate for now. Okay? What about a minus a? Caleb? It would be. If I have an apple and I give it away, I got nothing left. I know. Oliver?
Then, what's the difference between knowing that one thing is that minus that, or it's that and then a negative one?
So the minus is the same thing as is a negative term, which is why we're subtracting it.
So that could also be a negative a?
Mm-hmm. So an a and a negative a gives us 0.
This is why I don't like math. It's so confusing.
To keep track of, isn't there? All right, in your notes, you've got this guy. Let's fill it in. All right, so at the top, we need to give ourselves the definition. Combining like terms. We said like terms have the same two things. What two things do they have to have the same? The same variable and the same excellent exponent. Same variable, same exponent. And then let's try some. So on the bottom we have 2x plus 4x. 2 xylophones plus 4 xylophones. I have 6 xylophones.
Why is X just such popular?
3 square yo-yos plus 7 square yo-yos. We have 10 square yo-yos. You ever seen a square yo-yo?
Yeah.
They're so cool.
Oh, usually yo-yos are circular.
Kidding, I don't know that that's actually a thing.
Wait, is that it?
I don't know.
Picture one mode.
Sure.
I can make one.
Yeah.
4xy. So 4 xy yo-yos minus a xy yo-yo. 3 xy yo-yos. Now I'm just making things up. Oh, this next one, real cool. 5 square xylo yo-yo cubes. And 2 minus 2 square xylo yo-yo cubes. Cool. I know. Yeah, I don't even know what I was saying. Yeah, just like that. Good. Try the other 4 on your own. See if you can do the right-hand column on your own, and I'll stick answers up here in a minute.
I don't like those yellow.
I know the yo-yo cubes are a little tricky.
I don't like the
You're trying the 4 on the right on your own. All right. Go ahead and try, or check those other 4. Now, for this bottom one, you could have had m squared, or you could have put the 1 there, 1m squared. Either one, they're the same thing, so I don't care how you write that. Okay? How do we do on those 4?
Good.
Good?
I got all that.
Okay.